Hello and welcome to the Introduction to Astronomy. Um, my name is Mohi Saki and I will be your course instructor for this astronomy course. This course will be a very short and compressed course. It will only last for 4 weeks. So we have to compress all of the materials of a regular semester into 4 weeks. So it will be extremely challenging in terms of time and the material that we will cover. I usually start with a little bit of introduction about myself. I got my master degree in astrophysics from University of Missouri in St. Louis in 2017. I got my PhD in astronomy in May 2021 from Missouri University of Science and Technology. We will cover 11 chapters of this book, and we will not be able to go to much details of the topics presented for this course because of time, but we will go over the materials that, are the most important in each chapter, and part of your duty or part of your job is to go on your time when you're reading the chapters. You need to go on to much further details. So I will provide the broader view for you, and you need to go and understand the details when you study the chapters. Now, this is an introduction to astronomy. We cannot go to a lot of complicated details. In terms of understanding our universe, we need to have a lot of math background in order to understand, to easily understand what we're talking about. So, since this course is only the introduction, and I don't think that you guys are coming from, all of you are coming, some of you might, but not all of you are coming from a very rich um, mathematical background. So we cannot go to many details because math is preventing us. However, I expect you to have some basic knowledge of math. In order to be successful in this course, you need to follow the syllabus and the course schedule. I have them on Canvas for you, and please go ahead and read the syllabus very carefully. It's very important. I think the most important step in understanding this course and being successful in this course is to read the syllabus very carefully. Know what I expect in this course. Know how much time you need to spend. Kind of manage your time. Um, you know, um, do not let everything, kind of divide your time into reasonable sections. For example, on Monday, I spend 2 hours. On Tuesday, I spend 2.5 hours, and so on. So don't put everything for the last minute. You cannot be successful if you do that. Not only in this course, is in any other course, even if you're taking it in person and in terms of the regular semester. Um, this course is fully online. Um, However, it is it is designed in a way as if we are meeting in person, meaning that you need to spend time, read the materials, do the homework. Uh, if you have a writing assignment, you need to start writing, and so on. And you have my email address. It is available on course page and on syllabus. So feel free to email me if you have any questions or concerns. I highly encourage you to read the chapters before watching the videos. It's very important. So I will go over chapter one, or first part of chapter one today, but you need to read the materials before watching the chapters. Well, if you do that, the materials that you have already read, uh, you will have a better understanding of those when you are watching the videos. Um, so without any further ado, let's go ahead and jump on chapter one and see what it's all about. So a modern view of the universe. So exciting. Let's see what we're talking about. So what are the goals? One of the goals of this chapter is that we wanted to know our place in the universe and how big we are. Are we really big? Do we have an infinite universe? Can we really see the end of the universe? Um, If so, where are we exactly? Can we identify that? Do we know how small or how big we are? Let's talk about that. So, in other words, we really wanted to know cosmic address. We wanted to know where in the universe we are. And our knowledge about the universe is pretty small. We don't really know much about it at this point. We know we think a lot. We are discovering things, new things every day. If you go to physics.org, if you go to NASA website, you see new things every day. New comet missions, new star missions, new things, scientific discoveries every day. But in terms of understanding everything, we at least we know that we don't know much, and that's a good point. In terms of where we are in the universe, at least we know that we have billions of galaxies. So if you start from our home planet, which is Earth today, 2,000 years from now, we might have another home planet or two home planets. We don't really know. So if you start from Earth and we kind of zoom out a little bit, we see that we have 8 planets, 4 rocky planets, and 4 icy or big giant planets. And if you zoom further out and kind of go out of the solar system, we see that we are in a cluster of other stars near us. And that cluster is part of a Milky Way or Milky Way galaxy, our home galaxy. And in our home galaxy, we only have a specific section of the home galaxy or our galaxy that is habitable. In other words, it's not really dense, there are not many collisions, and it's not really far away, it's not really cool. And we call this region the habitable zone or habitable region of our own galaxy. Every galaxy has one. So our home planet, our own solar system, is located in this region. Our own galaxy is part of a local group. The local group is a bunch of galaxies that are interacting with one another through gravity. Okay? This could be 10, this could be 30 galaxies. Each local group is different. We are part of a local group. The way that we recognize these local groups is through the interaction using gravity. If we zoom even further out, we end up in a local supercluster. This includes hundreds of galaxies that are not necessarily um, interacting with one another through um, gravity. Any two objects in the universe interacting with one another through gravity, but they are not. They are still these objects in a local supercluster. They are still moving away from one another. If we zoom further out, we end up to something that we call universe, or the background image here is kind of a rough estimate of what we think it looks like. Okay, to me it looks like a nerve system as well. Everything is connected to one another to some extent or some way. So uh, if somebody asks you what is your cosmic address, there it is. Start from um, your planet home, and if you zoom out, you end up to some picture like that. All right, so in our local, in our own solar system, what do we have? We have a star or stars. The best one is the one that is keeping us alive is the sun at the center of our solar system. It is a large glowing ball of gas that generates heat and light through nuclear fusion. And we'll talk about this in chapter 11 and what the nuclear fusion is, how the sun is doing it, what type of stuff is happening inside, causing it, how much time it will take for a photon that's being created at the center to travel to the surface, what's happening inside the surface, things like that. We'll talk about it extensively in chapter 11. We also have planets, and these planets are either rocky planets like Earth or Mars, or they could be gaseous planets or icy planets like Jupiter or Uranus. These are moderately large objects that orbits a star. It shines by reflected light. So they don't shine, they're just reflecting. If we see the Jupiter, it's because it's reflecting the sunlight to us. If you see the moon, it's because a moon is not a planet, but it's because it's reflecting the sunlight to us. And these are um, big enough that they have enough self-gravity to be round shape. Okay, so in other words, if it was just a piece of rock in the universe, it doesn't have enough gravity to be round. But a planet and a moon is experiencing enough self-gravity to be uniformly round in all directions. Okay, in other words, these top layers that I am showing are putting pressure in the down layers, causing it to look round, in a round shape. Moons or satellites, we normally never call them satellites. Satellites are mostly referred to the man-made materials that are rotating around the Earth. But moons or satellites, they are these objects that are still big enough to be round. They have enough self-gravity to be round, but they are relatively very, very small compared to the home planet or compared to the planet that they are rotating around it. For example, this is Ganymede and it's orbiting Jupiter. And as you can see, it's not really that big. It's like and this size is 500 kilometers, so it's not really. I mean, it is big enough compared to our moon, but it is not really big compared to, for example, Mars or compared to Jupiter itself. We have asteroids. This is asteroid Matilda. If you go to astronomy conferences, they usually give out the 3D printer um, of these objects. So these asteroids are just rocky stuff. They're relatively very small, and they are mostly found between the orbit of Mars and Jupiter. And they are having a random shape. They don't necessarily are. Some of them might be completely spherical. Some of them are not. They are just, they collide with one another a lot during their lifetime, and they break to pieces, and they're coming in random shapes. They don't necessarily, they're not necessarily round or spherical. Comets, that's another thing that we usually see. These are, we only see comets when they're getting close to the sun because the sun is baking them gradually, meaning that when they're getting close to the sun, they start to form an atmosphere around them, which you can see here. Okay, and this is called coma, and coma is a Latin word for hair, because Asian people think that it looks like a hair as if somebody is running, and the hair, and this looks like a hair of someone, someone running. So, and we were still keeping the same terminology that they were using, so we call this coma. In fact, comet is coming from coma. They usually get two tails. One is the plasma tail, which is the gas tail. The other one is the dust tail, and they come from all different orbits. Um, some of them are very short, have a short orbital period. For example, Comet Anki has about 3.3 years of short orbital period. They have a short orbital period, and some of them have thousands of years of orbital period. If they go and we watch them, by the time they come back, we will never be alive, 7,000 years. For example, I watched a comet, observed the comet back in 2017, and the orbital period for that comet was 7,561 years. So by the time it comes back, I won't be around to watch it again. Solar and stellar system, or star system, is a star um, and all the materials that are orbiting around it. That includes moons, comets, planets, asteroids, and so on. Whatever that's rotating around a central star is called solar or stellar system. Nebulas, these are usually gas and dust, and they are um, in between the stars. Okay, so uh, in our solar system, because of the solar wind, we do not have gas and dust left behind. And we'll talk about it in chapter 6 as why we do not have hydrogen gas anymore between Jupiter, for example, and Mars, right? We talk about those. But in the universe, we have areas that are we call it clouds of gas or clouds of dust, and they are called nebulas. And Galaxy, it's which the book called it the Great Island of the Stars in the space, which is true. For example, this is M31 Galaxy. It holds together by gravity, and they are orbiting a common center. We believe that there is a one or multiple black holes in the center of the galaxy, um, and more than 50% of the mass of a galaxy is governed by dark matter. Um, these are the materials that do not shine. We don't really see them, but we understand them using their gravity. We know that they are there because they are showing some gravity to us. Um, for example, M31 has billions of stars in them. So there are billions of stars in one galaxy, and there are billions of galaxies in the universe. So the universe is a sum of total of all the matter and energy there is. Everything within and between all galaxies. So anything that is out there, we call it the universe. And one of the physics rules that we know, or one of the physics laws that we have, is um, the sum of total of all matter and all the energy is conserved, meaning that the amount of them will be conserved. Once it's started, and once it will end at some point, this amount will never change. The amount of matter and energy is always conserved in our universe. Okay, so this was part one of chapter one. I will go ahead and continue with part two. Stay tuned.